Uh, in the previous session, we have seen instantaneous center method to find out the velocity of different mechanisms. And there we also applied the same instantaneous center for the different previous year questions, especially from the GATE examination. And here in this session, we are going to find out the same velocity for the mechanisms using the different technique, that is a relative velocity method. This is also called as a vector analysis of the velocity of different mechanisms. So since we said it's a vector analysis, so first of all we will deal or know something about vectors. Vectors. So we already know that any vector is represented like this with a arrow mark. So length of this vector gives magnitude of that particular parameter. For example, if this in this session we are representing this vector velocities with this vector. So for example, this is the velocity. So the length of this vector gives the magnitude of this velocity, and this arrow mark gives the direction, in which direction it's moving. For example, this is O and this is here in this direction. In this case, this velocity V is acting from the point O to towards A, and this orientation here, this is a horizontal. So this orientation of the vector give in the sense of the velocity. What is the sense of the velocity? That means in which direction it's a acting. So here in this case, this velocity is acting in the right direction horizontally from a point O to towards the point A. So that's the meaning of any vector. And in the previous session we have already seen this absolute and as well as relative velocities, and again I would like to touch upon quickly. So there we have taken a case where this is the earth, and the earth some rail is, we have taken a rail, this is a rail, and for example, if this is going in this direction with a velocity Vr, then what is, and we already mentioned that there is no absolute velocity. There is no absolute velocity. If you strictly speak, there is no absolute velocity in the universe. But we always make something as a reference, and we always try to find out the velocity of the other object with respect to that reference point. So here in this case, most of the time we consider Earth as a reference one. So when you consider Earth as a reference one, then we take velocity of the Earth is equal to 0. So what is the velocity of the rail in this case? So that is with respect to Earth. So whenever I say, in all these cases, whenever I say absolute velocity of any object, then that should be with respect to your reference point, and here in this case it's a Earth. So this is going in this direction, so that is called as a Vr. So absolute velocity of the rail is Vr. Rail is running, moving in this direction, and inside a man he is also moving, for example, in the same direction. So this is the velocity of the person P. So now can we say absolute velocity of the person Vp? How can we say absolute velocity of the person Vp? Because he is not directly walking on the earth, which is a reference plane here, but instead he is walking inside a rail. So first of all, we shift the reference plane to rail, because on whichever platform the person is running, or any object that you intended to find out the absolute velocity, you find out on which platform is running or walking. So here this person is walking on the rail. So you shift reference plane temporarily to the rail. So what is the velocity of this person with respect to rail? So that can be written as velocity of the person with respect to rail. This is the velocity of the person with respect to rail. Again you shift back your reference plane from rail to earth, but here rail is not constant. If it is a constant, then simply here we get 0, but instead this rail also moving with some velocity. So this reference plane that we shifted from earth to the rail is not constant, but instead it's a moving. So what is that velocity? That is nothing but the velocity of the rail. So velocity of the rail with respect to reference plane earth Here we need to write earth, but earth we consider always as 0, so no need to write 0. So whenever I say Vp, or simply this is a velocity of the person with respect to earth, or whenever I say simply Vr, that is velocity of the rail with respect to earth, but in this case earth is reference plane, so no need to write this E again and again. So here that is how we have written this one. And here this value, this positive, because the both are going in the same direction. But if the person is moving in the opposite direction, again we will get, instead of plus, we get a negative direction. So in the previous case, the person is moving inside the rail, so that's why how we calculated. So velocity of the person equal to velocity of the person with respect to rail, because he is moving in the rail, plus velocity of the rail. That's how we calculated, because the person P inside, here P inside R. For example, if P is not inside R, and this is a platform, that means nothing but earth, and this is a rail, this is moving in this direction, and person also on the platform. See, for example, person is on the platform, and he is also having some velocity. So for example, if he is going in the same direction, then here in this case, what is the, this is the Vp and this is the Vr, and here in this case, what is the absolute velocity of the person? That is simply Vp, because he is moving on the earth, he is not no longer moving on some other object, but directly moving on the earth. But what is the absolute velocity of the rail? That is again Vr, because rail also moving on the earth. So relative velocity, here in each and every case we are comparing velocity of any object, for example person or a rail, with respect to some reference plane. So that is what relative velocity. But here this velocity of the person is with respect to earth, and here this is absolute velocity of the person and this is absolute velocity of the rail. Now I wanted to find out what is the velocity of this person with respect to this rail instead of ground. So that can be written as V P R. So velocity of the person with respect to rail. So this vector, velocity vector Vr is going in this direction. This is going in this direction, and Vp also going in this direction. This is a Vp, and this is Vr, and this is a Vp. So both are going in this direction. So this component will give Vpr. Assume that both these objects are moving at the same velocity. Then what is the velocity of this Vp with respect to Vr? It's a 0. Relative velocity of the Vp and Vr is 0, because for all the instances you feel like both are not moving, because the distance is always same, because they both are moving at the same speed. So that is nothing but this is velocity of the rail or velocity of the person minus velocity of the rail. Why? Because here in this case both directions are in the both velocities are in the same direction. So that's why we write like this. For example, if this Vp is moving in the opposite direction, in this direction, then this is a Vr and this is a Vp. So what is the relative velocity between these two? Vpr equal to what is the Vpr? Velocity of the P with respect to R. That is, this is moving in this direction and this is moving in the opposite direction. That means velocity will be added, because distance is very much increasing. In the previous case, it's a since they are moving in the same direction, not much distance is added, but here distance is much more in compared to previous case, because it's going in the same direction. That means distance, velocity is proportional to distance. That means velocity, relative velocity should increase. So here Vp plus Vr. Most of the problems that we deal are in the planar mechanisms, and instead of randomly choosing earth, here we take one reference plane. In on the earth itself we take one reference plane, that is a xy plane, and that is fixed at a point O. So this is the origin point, and if I choose any point here, let's say this is a point A, then what is the velocity of that point from the O? This is the velocity of that one, and this is represented as a VA. And if I take some other point randomly at a point B, so what is the velocity of this one? Absolute velocity of that point B is a point joined from the origin, that is a VB. And we know VA and VB. Instead of absolute velocity, if you want to find out a relative velocity, simply join these two. So this is the velocity of the B with respect to A, because it started from the point A. So here if you want to find out velocity of the B, what is that one? That is directly by measuring the from this point O to the point B. But instead you can measure the same, you can reach this point from by traveling along this line and then along this line. So that is a VA plus VBA. That means what is the velocity, absolute velocity of the point B, that is relative velocity of the point B with respect to point A plus absolute velocity of the point A. Otherwise this can be written as relative velocity of the point B with respect to point A can be written as absolute velocity of the point B minus absolute velocity of the point A. If you have a arrow mark like this, then instead of plus here we get negative, so that here we get a positive. So it's all depends on the in which direction these two are written, or this arrow mark is there. Linear velocity of any links. So again here I will consider a link. So this is the link, this is a point A. So we have already seen the what is if it is rotating in the clockwise direction with the angular velocity omega, what is the velocity of this one? This is a VA, and that is perpendicular to the link. And if I consider one more point here B, what is the velocity of this one? This is a VB, again this is also perpendicular to the link. That link means the point joining from the B to the rotational point, that is O. And we have also derived that this value of VA equal to, if it is the length of the link is known, then omega into OA. And what is the velocity of the B? That equal to omega into OB. So if I write VB by VA equal to OB by OA. So from this equation we can see that velocities, that means linear velocities of any of points on a link is proportional to the only distance of that particular point from the rotational point. So we need to remember this also, because here omega is constant for all points in a link. So we need to see that, and we have already derived this one, how BA became perpendicular to OA. What is the relative velocity between point A and point B? So again we will go by the vector method. So I will draw, this is the, for example, this is a point O, and this is the VA, and this VA, why I draw horizontally, because here this is going horizontally, and VB also going horizontally, so this is the VB. So both are going in the same direction. So in this case, what is the velocity of the point A with respect to point B? That is a nothing but difference between these two vectors. What is the difference between these two vector VA minus VB? So this is the absolute velocity of these two, and this length, if you cut this one here, this portion is representing a relative velocity between the point A and B. So if you observe this portion also along this direction, that means relative velocity of the point A and B is perpendicular to the line joining point A and B. So this has asked, in the previous questions, that what is the direction of the relative velocity between any two points. So that is a perpendicular to the line joining those 2 points. So as shown in the figure, I have taken one more link having the point A and point B with velocity VA and VB. But in the previous case, this link is fixed and it's rotating about a point O. But here instead it's not fixed, but still it's moving in such a way that it's instantaneous center is formed at O. At this instant, it's rotating about the point O, and its velocity is Va and its velocity is Vb. And what we are trying to do is we are trying to show that relative velocity of the Vb or relative velocity of the point B with respect to point A should be perpendicular to this link. That's what we want to show. And here this is a rigid link, that means it's inextensible, so it cannot be extended or contracted. And if I resolve these forces, resolve these velocities perpendicular and parallel to the link. So this is a perpendicular VAP and this is along the link. So this is a VA along the link length. And again, if I do, this is along the VB, this is a perpendicular to the link, and this would be along the VBL. But I said this is a rigid body or inextensible. So when I say inextensible, the velocity of the point A along the link should be equal to the velocity of the point B along the link length. Why? Because if the velocities are not equal, then it travels, the distance traveled by point A is not equal to distance traveled by B. That means it may undergo extension or the contraction. So that means this no longer as a rigid body. So here VAL equal to the VBL. So that means the velocity along the link, velocity of the 2 points, velocity components of the 2 points along the link length are equal, and we have this one. So what is the relative velocity? What is the relative velocity of the B with respect to A? That equal to relative velocity of the B minus velocity of the A. But what is the velocity of the B? That has 2 components. So if I assume this as a I and this as a J, so that is a VAPI, VBPI. Here also this is the I and this is the J. That means if I consider the reference point here having the x-axis like this and the y-axis like this, and this is 0. I have randomly chosen, so we can choose that only for the sake of understanding. So whenever we take x-axis, generally the vector along the x-axis is I, and whenever you take y-axis, the unit vector along the y-axis is J. So I am writing this in a vector form. This is a VBP J I plus VBL into J minus VA. What is VA? VAPI minus VALJ. But we know VBL equal to VAL, so this will get cancelled. So again, this is simply VBP minus VAP into I. I means unit vector. So we have this vector, this relative velocity between point B and A is only along the unit vector I. That means it's only along the axis x. But again, this axis x is perpendicular to our link length. So here we deduce that relative velocity of any 2 points is always perpendicular to the line joining those 2 points. So that we need to remember, because sometimes I think last year in 2014 directly they asked this statement in the gate examination.